So while we are waiting, anybody want to chime in with something that you really want to learn through this, coming out of this session?
Well, I can kind of echo what I put in the chat, which was, what Jane was talking about earlier around just PII and how can, with all of the rules and regulations in place, how do you find ways to actually identify PII or extrapolate good insights, and still do it in a way that is legal and fair and equitable and all of those things.
Yeah, and the what they've done in the past with this kind of data is they've aggregated it, and so they aggregate it such that they take most of the interesting information out of it. So you've got to maintain the utility of the data at the same time as creating a privatized data set.
Right. Thanks for that. Yeah, I just think we don't want to lose the insights, right? If we're taking out too much of the stuff and aggregation.
Yeah. And so we've been working, as I mentioned, on differential privacy, but it's very hard to apply to mobility data. Differential privacy is really good for, record level data like healthcare data. So trying to understand how to maintain the spatial information is the challenge, particularly in my area, which is mobility.
Okay. Got it.
That's a good point, Jane, because I know on the building side, there are companies working on differential privacy and creating buckets into which you can put the data in there, anonymize it. So, but you're right, with mobility, it's much harder.
Yeah, it's mobility is much harder than it seems once you get into it, because there's so many systems of systems with all those pesky humans in there as well.
Hey, I think we are at the hour. Travis, any update? Are we ready to go?
Double check with Eric here right now.
Okay, we do have 54 people, so that's a pretty healthy group.
Ram, Eric's giving me the thumbs up. You're good to good.
Great, thank you. And if Jeremy comes in at any point, we'll let him chime in too. So for those of you joining in into this breakout session on AI and connected communities and smart cities, welcome, and thank you very much for your time. So this is part of EPRI's AI challenge, where we are looking at the application of data and artificial intelligence within the energy community. And this is one of the 5 work streams, grand challenge streams, which is looking at the edge of the grid, looking at the collection of data that's coming mostly from the customer side and trying to figure out how that connects and engages with the energy system itself. So I'm Ram Naranamurthy. I'm the lead for the buildings program at EPRI, and I'm here helping Jeremy with coordinating and starting up this work stream of the Grand Challenge. And we have 4 really great speakers, people who've been working in this area for a long time. And I will let them introduce themselves when they get to their presentations. But just a very quick overview. So Zoltan Nagy from University of Texas he works in the Intelligent Environments Lab. He leads the lab. And the interesting part about Zoltan is that he actually came from a robotics background into buildings. So very interested to hear his perspective. Jane McFarland from UC Berkeley. Jane is in the transportation side, which again is part of our communities and getting to low carbon communities. And Jane's going to be talking about all the intricacies of working with data on transportation. Jan Dragona with PNNL is also looking at the intelligent buildings area. and he's going to be talking about how to use large-scale data and adaptive intelligence to be able to improve our building stock. And Pen Zhao from EPRI is working on the AI initiative within EPRI, looking at building controls and sensor data and trying to understand how we can use that to better operate our buildings. So again, welcome everyone. The way, so you are now in a WebEx meeting, which means that you're all unmuted. You're all able to talk and ask questions. We would love for you to introduce yourself on the chat. Please put your name down, where you're from, your affiliation, and if you can, something that you're really interested in taking out of this session today. And also at the end, you'll feel free to ask questions after the presenters go through their presentations. We'll have maybe a minute or two for questions, so clarifying questions then, and then you can see the agenda at 50 past the hour, 1:50 p.m. for those of us on Pacific time, 4:50 p.m. for those of you on Eastern time. We will have an open discussion. And then following that, we will talk a little bit about how we are going to carry this forward and future meeting schedule, etc., and what we would love to get from you as practitioners in the space. So very quickly, I'll just do a quick overview of some of the work. So I lead the buildings program at EPRI, and some of the work we do in the buildings area is focused on decarbonization of the building stock. And one of the things that I wanted to emphasize is that buildings today, they contribute about 39% of the total carbon content or the carbon emissions, both from construction practices as well as from operations. And so we tend to focus a lot on how do we reduce that carbon, right, within our building stock, because we have targets for 2040, 2045, 2050, depending on where you are and which government target you're looking at. But within that, right, what we try to do is look at how we can decarbonize our buildings. We look at different decarbonization strategies, whether it's through electrification, whether it's through a mix of electrification and other fuels, or even looking at how do you actually wait for other options to evolve, whether it's low carbon fuels, etc. So we focus a lot on, okay, here's the carbon content. How do we reduce the carbon in our buildings? Flexibility is a big part of that carbon reduction strategy. And then looking at how we can actually drive down the carbon over time, especially as the electric grid gets cleaner and low carbon, right? So when we think about decarbonization, we think of two big drivers for decarbonization. One is our clean energy generation targets, which are very prevalent. I think around what we estimated was around 85 to 90%, 85% as of end of last year, probably growing now. 85% of the US population has some kind of a clean energy target, whether it's through a utility, whether it's through a state, whether it's through a city, etc. But what that means is that there's two types of targets, right? One is economy-wide decarbonization. The other one is looking at grid decarbonization. And in a sense, grid decarbonization is a big driver for us to look at more flexibility from both our buildings and transportation. Because as we decarbonize the grid, we are going to need more flexibility in our energy use, both and possibly on the energy storage side too. But these are two sides of the same coin. And that really drives a lot of the work around controls and sensors in our building stock. Now, on the other side too, there is efficiency benefits and customer engagement benefits from the work that we do on controls and sensors and from the data that comes from that, right? So I think our speakers will talk to all these different aspects of how the data and more intelligence in our buildings, in our transportation, can actually help with these decarbonization goals. I'll quickly skip through it. When we talk about buildings, we talk about electrification challenges. We talk about resilience. That's a big priority. And we talk about how do we equitably transform our building stock. It's very important for us to remember that as we decarbonize our buildings, we really need to also focus on the affordable housing and the ones who cannot afford the whole transition, right? And so a big part of our research that we do actually focuses on looking at affordable housing as a leading edge of decarbonization. And what that leads us to is looking at these different archetypes for sustainable smart communities. There are a lot of different examples. This is just some of the work that we've been working on over the last 7 or 8 years, but there's a lot of examples. There's a lot of effort going on into these connected communities, and I'm hoping some of our participants can talk about it a little bit more too. But underlying all this work on connected communities is data, right? Data of different forms, data from different sources, whether it's end-use devices, building control systems, from our transportation network. How do you pull all that together? How do you create more sustainable communities? For example, if you're doing smart thermostats, right? There's probably 10 to 20 million smart thermostats out there, each of which is pushing out a bunch of data every minute, every 5 minutes, right, to different clouds, right? And so there's a lot of data that we can use, potentially use, to understand what is going on in our buildings. And our speakers will talk about how they're using the data and what they're learning from it. So with that, let me hand it off to our first speakers. But the overall big picture is, let's look at the data. Let's look at communities as aggregations of buildings and transportation systems that provide the data. And let's figure out how we are going to use the data more intuitively, more smartly, to be able to advance our zero carbon communities. With that, let me stop sharing and hand it off to Zoltan to talk about the research he's doing at University of Texas.
Okay, thank you, Ram. Okay, here we go. Welcome, everyone. Hopefully everybody can see my screen. I'm Zoltan. I'm faculty at the University of Texas at Austin. I'm directing the Intelligent Environments Lab. My research broadly, as Ram said, brought me from intelligent systems in general, from robots, over a little escape on into the architecture school, on where I learned a lot about buildings and big challenges about organizing buildings and controlling the energy systems, and also the big impact they have on our built environment and opportunity we have in decarbonizing our built environment using buildings. And so now my group focuses on two aspects. One is the pesky occupant, as Jane mentioned it before. It's the part where we're looking at individual zones, very detailed, and try to understand how we can deal with building interaction, occupant building interaction, and learn from that in a non-intrusive way, and then introduce knowledge from that in building operation in order to improve the energy efficiency without annoying the people. I will not talk about that part. Here today, I will talk about the other end of the scale, which is, and we'll talk about communities, many buildings, and how they can form sort of like a combined response to the grid and provide the flexibility measure. And so I will present this tool that we generated at CityLearn, where we can create these questions and study them in a sort of like computational environment. So what it is a gym environment that allows us to do controls, which is what we're focused on the most. What it is basically a storage control problem. Assume buildings that we have in there, we pre-compute the loads that are relatively stochastic, so they're not all using the same thing at the same time. It's not just multiplied, but you create a sort of like environment that is, you know, random-ish. And then you simulate, and then you can understand how the systems are being used, and then you can control those systems. And the way we envisioned it when we built it was to, you know, think about this. Some of these questions that came up already before is, well, how much information do we want to share between the buildings? Do we want to create the complete coordination where everybody knows everything? Do we want to see how, you know, nobody knows anything about everybody else? Do we want to create this potentially very detailed environment where every building may have its own pricing scheme when it interacts with the power grid? So all these kind of things we can do. It's not a physical simulation in the interaction, so the buildings are not physically co-located anywhere in this model, but you could emulate that in this environment. So a lot of the text is on the website, citylearn.net. There's every detail is there. It's open source, so you can can go and check it out for more. And I'll show you an example of what we can do and expose one of the problems that we will see when we think about grid interactive buildings and optimizing GUs. So like I mentioned, this is the little bit more detailed overview. We have chilled water and domestic hot water storage, and we have battery storage for now. We also have EV systems planned to be put in, which in our model, essentially batteries that show up on a certain schedule as a resource. So that's another layer that we can integrate. The option for solar arrays is in there, also heat pumps, electric heaters, so that we can, and the systems can be turned on and off and sized the way you want it. So you could simulate undersized systems or oversized systems, and so, or storage, or just, you know, selective buildings having PV and storage and so on. So that's kind of like the idea. And so that's why we said, well, let's assume the buildings have a certain load that is given. Let's assume they have a certain occupancy pattern, the scheduling and all that, and that is not changed. And let's focus on the systems and how we can control the storage. So we have to shift loads basically. So, and with that comes a very important caveat, because a lot of these problems always assume that the thermostat is a resource, and we don't assume that. So in our problem, the thermal load is always satisfied. Occupants are never complaining. And if basically they don't have enough storage, you will get that from the power grid. So that is usually looked at as a constraint to be satisfied, and then you look at violation of set constraint. But in our case, it's always maintained, so there is no comfort issues, assuming the simulation is accurate. Smart caveat. So why do we do that? This is from the DOE's Grid Interactive Roadmap, the three sort of ways or generations how we can create interactive buildings. The one that's been done all this time is create more efficient buildings that use the same energy, use less energy at the same time as before. Then when you start in the middle, when you start integrating PV, so you get this duck curve in the middle, have potentially surplus in generation, and then you have this ramping problem at the end of the day. A lot of potentially bad power plants have to come on to meet this demand when the solar goes away. And so where we're trying to get, or ideally, is this more horizontal curve, the blue one here, where we move loads around during the day or drop load from the grid, so that we have sort of like a more constant profile throughout the day, and that becomes a lot more predictable. And the point of this is, this should be on a sort of aggregated level. It doesn't have to be on every building, right? It can be on 20% of the buildings may be able to provide this in a whole neighborhood. That's kind of like the things we could. So the question is, right, how do we get to this sort of behavior from this relatively large with the peak? And so my presentation is about, like I mentioned before, storage and control. And in particular, I will show you results from one particular approach, which is Model 3 RL, with the idea that we can adapt to a certain behavior over time by using sufficient data. So that's kind of like where this is going. So without going too much into detail on RL, the whole idea is to model the control problem as an interaction between agent and the environment that it's trying to control. It receives a certain state as input, that is your sensor readings, your data, or some kind of aggregate of those signals or derived values, and then it can do stuff to the environment, which in our case is charging or discharging storage. And then based on you as a designer, you design a reward function to basically give a feedback to the controller whether the action was good or not. So this is a very important topic, the design of the reward function. But essentially, over time, the idea is that with the agent will maximize its reward that it's seeking, so it will try to find the actions that for given states will maximize said reward function. That's the optimization process. Typically, the way these problems are set up, at every time step you get a reward, and that's in our case an hourly step. It can be sub-hourly as well if you wanted to make it, but currently we're doing sub-hourly. But one challenge with that already, as you can tell, is that some metrics that we're looking at from the grid perspective are not necessarily an hourly affordable, right? So maybe some are known at the end of the day, like the daily peak. Some may be only known at the end of the year, which is like the total peak that you had in that environment, or in that neighborhood. And so it's very hard to optimize for such rewards, such metrics that you're trying to achieve. So the question becomes, what is a good reward design for what type of metric you're interested in? So it's a two-layered problem that I addressed it at all. And this is not an RL problem, this is a general problem. What is it that the grid considers a good KPI, a good metric for an environment? And then what is it that we need to give the controllers, no matter how they're designed, what is it that we need to tell them to optimize for in order to achieve those metrics? So here's the example that I'll show you. This is 9 buildings. These are, I think, DOE standard buildings. So, reproducible. 5 of them are multifamily here at the bottom. 4 of them are commercial. It's roughly 50% load on residential, non-residential. In this particular example, 4 of them have solar PV. And all of them have the storage setup. So you don't have to read this, but this just to give you an idea, like all the sensor technically we may have, or some outlook into the future and forecasted temperature, for example, 12 hours ahead, 24 hours ahead, things like that you can use as input. And then the actions would be whether you're charging or discharging your 3 possible storage devices. Again, you can add more to this, you can remove some, you can study what the impact of these are, how often you update these, and what the impact of error is, and so you can just rerun the simulation model. Mentioned the reward function. So the simplest one that you can find is this one that we're currently exploring as we just began dabbing into this a little bit more detail, which basically is an efficiency function, right? You basically penalize the energy that you're using at every time step, except if the whole neighborhood generates electricity. So in the case where we would have complete solar generation, there would be times of days when you have a generation, a positive net generation, in that case, the electricity is not penalized. So this is the simplest one. There is a few things when you design these, right? How much information do you want to share between the buildings to generate that reward function? How much information do you want to share between the buildings to take certain actions? That might be interesting if you have a certain aggregator in between buildings and the grid, which can take those. And so all of this information flows is currently, at least for me, unknown and found. Once you start shifting loads, the value of that becomes also different. So how much money can you optimize for? What is the business model, or what is the value per hour at a certain time of shift? And more importantly, if everybody's able to shift, right? Because then everything kind of just changes. Down here, the current sort of like cost function or scores that we're looking at to evaluate, and the first 2 are sort of grid level ramping, so the energy change between 2 time steps, gradient, and then the load factor, the peak to average load, that sort of like tells us how uniform the load is. And the others are more typical ones, like the net electricity consumption, peak to peak. And then the carbon emissions, which for this example, because it is from Texas, we can convert to ERCOT mix level, and so you can immediately know what carbon emissions are, which is very similar to net electricity consumption sort of metric in this case. So to show you what the output is, we ran state-of-the-art algorithms. Yes, sir.
One question. I think if you can increase your volume on the audio.
Oh, will this be better?
I think so. Yeah. Sorry.
Okay.
Yeah, it's a little like.
No, that's good.
Okay.
Is it better this way?
Okay. It's better, I think.
Thanks.
Yeah.
Thank you. So, so here is the output of the 9 buildings aggregated, and these algorithms, you don't have to worry about those. These are all state-of-the-art multi-agent controllers. So each buildings would have their own, and then there's a certain way how they, combine the reward or share the reward, share some information between them. And so you see they all kind of like perform similarly. The gray curve is the sort of like the standard demand that the environment has. This is in Texas temperature, so the summer peak is pretty big. And then the black curve is one that you would get if you would, get in and really optimize your systems by hand, rule-based control. And that gives you quite some leverage. If you can do it, that's pretty good. And that is not often done, but this shows that there is some potential for, optimizing your own systems. And then the RL controllers do what we want, which is lower lower the peak, lower overall the overall energy consumption even further, and also, make it a little bit more horizontal by using some in the night of the energy to charge storage. And you can do this on the other, fall and winter, but the summer in here at least is a lot more important because it shows you the flexibility that you have. And it shows you that this is the one, like if you look at the green curve, you get very similar to the blue one that you out, and you can look at that and see there. So it is possible with, this is an optimized version. So this is not a live version that runs within a year and you have this. So in an optimized version, it is possible to get to an interesting behavior for the grid. And then you could start playing with things like, well, we need this, tomorrow, or we need this in 2 hours. And then you kind of like try to see what that would generate for the buildings or the environment, and how much you can really shift at that time. The thing that I wanted to mention, the reward function and its impact on the scores, you can see broken out here, is with this reward function, you can see that some of the scores, like the ramping one, is really bad because it's not optimizing for it, right? So you will not get necessarily into that behavior, or I should rephrase. You get into this behavior that you get here, so you see actually it's pretty good, but it's not reflected here, which is not good. So basically, if you just looked at this number, you would not see that you're actually doing what you're doing. So that's kind of like the important thing here, is that we need the indicators that reflect properly what is happening in buildings, and we need to be able to optimize for those and make sure that we can combine them in a way that is useful for what we want trying to achieve. If carbon emissions is what we're trying to optimize for, then that is what we should be having as a main reward, rather than the net electricity use, for example. And this is just showing the same thing, basically. Like, these two controllers exceed the reward, so they really make to learn stuff. That's kind of like what this is showing. But their overall performance on the average of all of these indicators is not better than the one, which is the RBC controller. So it looks like there is a lot of potential to play with this sort of like reward or optimization goal at every time step in order to push this towards further improving the operation of the buildings. And so this is why we're organizing this annual challenge, where we basically give out these, like, this is an open source environment, so we set a problem or create the buildings and the loads so that people can compete for it. And so this is a result of this year's challenge, 5 groups. And just very briefly, the only thing I want to mention is you can see that this group 1 here managed to get some pretty decent results, better than the state-of-the-art RL algorithms that I showed you, especially on one ramping here, which is a very interesting one in real life, right? Because you can really horizontalize that duck curve at that. And so we'll look forward to do more in this, and we'll do it again next year, perhaps with a different problem. This was the second instantiation of this challenge. But the idea is to get a community-driven problem here, right? So if you have a problem challenge, we can create it and then have solve it. Lastly, we're extending the system without going into too much detail. So I talked a lot about energy, but we're also looking into voltage control. So you have to downsample a lot more and look into voltage stability. So with Dr. Baker, who's leading the parallel session, these grand challenges, we're working on integrating a grid simulator on top of these, so the buildings could have like smart inverters and then focus on not just energy optimization itself, but also voltage stability, which is also an issue that will come up more and more. See how that is implementing, how that is happening. And then lastly, if you're interested in this topic, we're organizing this RL workshop at BuildSys later this year. Jan, who comes up soon as a speaker, was one of the program chairs this year, so we'll have a really great program coming up in about 2 months from today. We just finished the reviews, and we also have we'll have great keynotes, and we also have like a getting started sort of like session where these environments are introduced, ours and also another one, and then LBNL's Bob test approach, so we can really rally the community along this topic. It's called RL, but we're not that tuned to that. It's obviously comparing algorithms, and for the greater good is what we're trying to achieve. That's it. If you want to hear more, we have a YouTube channel because it's the 21st century. So if you want to see some of the details, some of past years, RLM edition papers, feel free to go. Some of our work is presented. I'm happy to have a chat. Thank you.
Thank you very much, Zoltan. And thanks for the great presentation. So just looking at the time, I think I'll move on to our next speaker, and we will address questions during the Q&A session. So Jane, I guess, yeah, you got it up. Thank you.
Having trouble unmuting there. All right. Good afternoon, everyone. I'm the Director of Smart Cities and Sustainable Mobility Research Center at UC Berkeley Institute of Transportation Studies. I'll note that my PhD was in AI many, many years ago, and it was when we didn't have large data sets. The ones that we have today are a joy to work with. So while machine learning is really hot right now, let us not forget that knowledge-based systems and inferencing systems are also an interesting approach to looking at complex systems. My PhD actually was in qualitative reasoning about dynamic systems. So interesting things you can do with knowledge-based. I think generally those are kind of referred to as physics-based as well. So lots of different approaches in this space. I'm talking about some work that we've done supported by DOE, Eames Group, specifically David Anderson and Prasad Gupta. What I wanted to talk about today is mobility, and that's mobility with an I. I'm focusing on AI techniques and the use of high-performance computing and analytics of large data sets for looking at urban transport on regional transportation networks. So the key here is the size of the road network that we're looking at. So mobility uses parallel discrete event simulation to simulate the traffic dynamics. It's an agent-based model. We've also implemented beyond just simulation, optimization algorithms that are that are used in the transportation planning groups to estimate loads on the network. And we use graph neural networks as a core modeling approach. So the platform produces very large data sets that estimate the network metrics at the link level, as well as aggregated statistics for the network as a whole. So for example, we can generate speed, flow, fuel consumption at link levels during a full day of mobility, as well as, aggregated statistics like vehicle miles traveled during the day or vehicle hours delayed at city level and regional level. And again, it's a region, not just the city. So how the cities interact is a key part of the system. The platform runs on the Lawrence Berkeley Labs NERSC Supercomputer Center. And by using these parallel discrete event techniques, we've made a step change in the computational requirements for a simulation like this. Often these kinds of simulations will run for weeks, and generally people don't simulate at this level of fidelity. As you can see on the left-hand side here, we can run a day of mobility for the Bay Area, which is a 1 million link road network with 19 million trip legs in only 4 minutes. Similarly, for the Los Angeles region, which is significantly larger, we can run 40 million vehicle trips across a 2 million link network in a matter of 6 minutes. So it's a huge change in what we can do from a simulation perspective. And then we also use real world data to drive the simulation. And we're building analytics capabilities that will provide the foundation for additional machine learning focused on building surrogate models that can replace the need for the supercomputer, so that we can deliver to cities so that city planners can have it at their fingertips. So I think this kind of capability is really important for city planners and operations to manage the complexities of next generation traffic operations. Particularly if we ever get to automated vehicles. I know it's a long ways away, but what are you going to do when you have control of all those vehicles and you've got to tell them where to go? And you'll create chaos on the road network if you don't have good control ideas at regional level. And in the meantime, connected vehicle control could likely be significantly improved by using these kinds of tools once we have the capability to simulate so quickly and investigate new control algorithms for moving people around a regional space. All of this, of course, with the goal of improving the quality of life in our cities and reducing the impact of our movements on the climate. So with these very quick compute times, we can start looking at all these different control algorithms. So one of the things on the left, you can see we also do the optimization, which is dynamic traffic assignment in a matter of minutes, which typically, if you only did it static, can take you 24 hours. But static traffic assignment significantly underestimates congestion. So we have the ability here now to start looking at all these different approaches to understanding how to route people through this network. And think about today we have a mix of control ranging from government controlled traffic signals, connected signals, corridor control, all the way to industry navigation systems. So there's the Googles and the Apples and the Here maps that are constantly redirecting individual vehicles based on travel time estimates coming from GPS information. So with the ability here to investigate a scenario in minutes, we can then propose new approaches to controlling all these vehicle movements and look for opportunities to aggregate movement or convert movement to other modes, like design bike paths that have a higher conversion of vehicle to bike. And again, all of this in context of the city goals, such as making sure that the congestion the changes that could happen as a result of a new control mechanism don't end up putting more traffic around lower income communities or around low income schools or the result or those kinds of equity issues. So here's a couple of examples of our output. On the left, you can see who touches the westbound bridge, westbound lanes of the Bay Bridge in the Bay Area. So the expansive reach of that bridge is shown here. Similarly here, the eastbound lanes of the Richmond Bridge. So you can see the different profile of how these bridges are serving the regional transportation. So this can be particularly helpful in examining the impact of network changes. In this example, we examined the congestion impact of the closure of the Richmond Bridge, which actually happened in February 7th of 2019, where some part of the bridge started falling from the upper deck down to the lower deck. And so we were able to simulate all the vehicle hours delayed on the major highways and the localized changes in the cities, which is the Richmond on one side, and everybody went, a lot of people went south to San Francisco. We also had the GPS data from mobile devices for that day. So we were able to kind of look at what were those humans doing during that process and look at it in context of the simulation we were able to build. I'll talk a little bit about that data a little bit later. As I mentioned, we use a graph neural net approach to modeling. So it's a physics-based model of diffusion to model how traffic will move across edges in the network. And this allows us to forecast traffic dynamics really well to like 2 or 3 miles per hour kind of precision. And it's the DCRNN itself is trained with a year's worth of real world data that comes off a Caltrans system of that are inductive loops in the highway. And it takes about 3 hours of wall clock time to tune the hyperparameters on the supercomputer to build this model. We've also demonstrated transfer learning with this model. So training on Los Angeles network with Los Angeles data and still able to predict Bay Area dynamics with Bay Area data. So that implies that the underlying modeling approach is strong for this type of problem domain. And our current research focus, which is I mentioned earlier, is really focusing on building a surrogate model from the large data sets that we can generate with mobility, and then learning the dynamics or codifying the dynamics of the network so that we can then be able to transfer this model off of supercomputer to traditional architectures. We also use machine learning with our GPS data. So I mentioned this earlier to find the GPS data as a real world data set. This gives you an example of what the data looks like. We run it up in AWS. We have a full pipeline that does all the data conditioning and all the work necessary to turn real world data into something useful that you can mine. And here we used it to understand where we think the traffic signals, traffic controls are, and particularly traffic signals as well as stop signs. So this is showing the results of that machine learning capability. And we're looking to use a connected vehicle data set that has about 10 terabytes of data if I can afford to buy it. And one of the challenges, which I'm sure we all know, is that security and PII is really important with this data, and that makes it really hard to get, and it makes it really hard to share. And so finding ways to privatize the trajectory data, mobility movement data is a really key part of kind of getting us to move forward in this whole space. And we are working on that. We have already developed a differential privacy approach to dealing with these GPS data sets. And I haven't really yet talked about those 19 million trips in the Bay Area that is kind of driving this simulation. So we load the network with those 19 million trips. They come from the San Francisco County Transit Authority travel demand model. It's a tour-based model generated by a significant effort based on surveys and a variety of demographics. And these models are really expensive to build. And we're often working with a model that's 5 years old, for example. So what we're looking to use is these very large GPS data sets to improve our understanding of current mobility and augment those travel demand models to reflect more of the current movements of the population. And here you see kind of the hot spots of mobility associated with work, going to work in the day. And then what we use this demand model is we learn from the demand model and try to tag the GPS trajectories with what we think their purpose is. Are they going to work? Or are they going home? Or are they going to lunch? And so we're using a model to help us then make inferences on data that does not have that information in it. And so here you see the machine learning tagging of the individual trip purposes. And on the left, you can see here kind of what we call stay points, which is where people tend to hang out in space and time, which gives us information about what they might be doing there and what the reason for being there is. You can combine that with land use and population information and demographics to try to reason about why human beings are there and what they might be doing next. And on the right is just an example of what the profile looks of the travel demand model and what the probe data profile looked like after our machine learning approach to tagging the information. So I won't go into detail on this. This is just the kinds of things that we can do with this mobility platform. So we can do this quasi-dynamic traffic assignment, as I mentioned, which is more of an optimization, which is not what's happening out there, because what's really happening out there is kind of a dynamic routing where we have found our paths to go places that we traditionally use every day to go to work. But we might have knowledge-based routing, which is, again, those pesky humans deciding, I think I want to just stop and get a cup of coffee today on my way to work, so I'm going to take something completely different, a different path than I probably should if we were trying to optimize energy or movement. So that's a much more detailed slide that's not worthy of going into at this moment, but I think this dynamic routing kind of approach is really more what's happening out there on the network. So what you'll see here is for the city of San Jose, hopefully you can see it well enough. These are all the trips in the city of San Jose that are associated with going to work in the morning from 6 to 7:45. And so you can see at the bottom there, this whole profile of everybody going to work around the 8 a.m. time spot, and then filtering down as the day goes by. So now you can start to think about where all these people are, why are they there, what are they doing, and you can slice and dice all of this activity and this human movement in terms of, you know, what are they doing and how can I support their mobility and provide the energy they need to get there, and how much energy they're consuming at that moment. And one of the reasons I'm really interested in the building side is that if you can start augmenting this with building loads, you can really dig into the impact of mobility on energy use and its impact on the climate as a whole. So that's a quick story about all of the AI type data analytics work that we're doing. Thank you.
Thank you very much, Jane. Great presentation. And looking at all those traffic maps, right, just reminds me of my daily commute through both the Bay Bridge and the Richmond Bridge. So probably a real reflection too of that commute. So
Yes.
So thank you. And again, I think since we are running a little bit tight, I'm going to keep moving, but we are going to, for the audience, please keep adding your questions to the chat. So we will actually use those questions when we get to the Q&A session. So with that, let me turn it over to Jan Dragona. Jan, you have the floor. Thank you.
Thank you very much, Rama. Thank you very much, Jeremy, for having me. I hope everyone can see my screen right now. Yep, perfect. So my name is Jan Dragonia. I'm a data scientist at Pacific Northwest National Laboratory. And today I want to talk about how we can use differential programming for modeling and control of building energy systems. So I will be focusing on how can we model and control individual buildings, as Jane already presented nice overview of how you can model network systems on traffic and how individual loads of the buildings can be coupled with these kind of systems, as well as Zoltan was presenting a great overview of how can you use advanced data-driven controls on modeling these multi-agent systems. So I will be presenting the recent work of our team at PNNL with my great collaborators, Elliot Skomsky, Soumya Vasist, Aaron Tour, and Draguna Vrabie. I want to start the story with model predictive control. It's classical engineering approach, which has lots of success stories in energy systems and in industry, coming from process control, automotive, aerospace, although high performance robotics. So this is proven reliable technology for this type of systems when you have reliable and accurate system dynamics model. So this is strong assumption, especially for buildings, because the challenges with the buildings is that we often have unknown or partially unknown dynamics, and purely physics-based modeling is way too expensive. It can take months to develop high-fidelity building physics model using manual labor, and it requires like army of PhDs to deliver this model. And what is even worse, every building is a prototype. You cannot reuse one physics-based model developed for one building to another building. So the story starts again when you come up with a different system. On the other hand, using only pure data-driven modeling lacks generalization, and you require lots of data. Another challenge when you already have your model, how do you compute this real-time optimization problem to solve this optimal control? There are issues with scalability, limitations of the computation on your control hardware, what you have typically on site on the edge, or parallelization and distributed optimization. So these are just two main challenges I want to focus on. There are way more challenges which come with application of the advanced control for buildings, but we believe these are like one of the primary challenges which we as a controls community or AI community can focus on and tackle currently. And we believe like that using differential programming together with model predictive control, which we call differential predictive control, can help us to tackle these problems. The idea is very straightforward, is to compute a differentiable closed-loop control system, which consists of the control policy, system dynamics model, and differentiable model predictive control like objective function. So when you have this differentiable program, you now can compute sensitivities to some distributions of your initial conditions, like what are the temperatures of your system. These are the references, constraints, or ambient temperature. And this allows you to run gradient optimization to optimize the parameters of different parts of the differential program. So you can optimize your system dynamics model to do system identification. You can optimize the control policy to learn how to control the system when you have learned your system model, or you can learn part of your objective functions or constraints if you don't know them beforehand. So let me give you a hello world example of how can you use this differential predictive control for learning control policies on this unstable double integrator system. So stability and constraint satisfaction are one of the primary features of the model predictive control, and that's why it has been successful in the industry. And we want to retain these advantages with learning-based approaches. So in this case, we formulate this differential predictive control as an optimal control problem when we are searching for learning the parameters of our control policy pi that maps control parameters to control actions that steer the behavior of the system dynamics model. In this case, we are given this linear system dynamics that is unstable, and we want to stabilize the system trajectories as given on top right figure and satisfy the control action constraints given at the bottom trajectories. So this is offline learning given the model based on learning the distribution of your initial conditions and how should you behave based on simulating this closed-loop dynamical system. To give you a little bit more intuition how it behaves during the evolution of the training, this is how those trajectories evolve of this simulated differentiable closed-loop system when we optimize it using gradient descent. So we see, like, at the beginning, the policy doesn't know what to do, but because we have a model, it can simulate the behavior, and over time, it can stabilize those trajectories while satisfying the constraints. So everything is now offline with relatively fewer number of parameters, and this could be solved under a minute on a CPU machine very quickly. So the advantage of having the model is not only provides you with some stability and constraint satisfaction guarantees, it also provides you with way more efficient learning in terms of the data requirements and number of parameters that you need to estimate and control. So now I want to show you how can you use this new technology for modeling and control of the buildings. From the building perspective, we typically are starting with some physics-based model, but we can also interpret those physical equations as differentiable equations. And this is just a high-level idea. How can we interpret, like, different parts of the building dynamics, which is driven by the building envelope, your building structure, the HVAC system, and behavior of the occupancy or ambient weather. We can compartmentalize them into different interconnected physical systems that can be modeled by different neural networks or hybrid physics-informed neural networks. So if we know some prior knowledge, like that buildings are dissipative systems, or we know that we have certain constraints on our HVAC system, we can impose them before we are going to train this physics structured neural state space model. And for the comparison, we did this study using first linear model, which is standard method for learning dynamical systems on the buildings, on this 20-zone building model, given real-time data from a real-world office building. And we are considering only 10 days of the training data, and the successive 20 days are for validation and testing. And what you can see with this linear model, that it can fairly accurately represent your training data, but further you go into the future, it starts to deviate, and the physics doesn't hold, and the predictions are basically useless for doing any control or forecasting. But when we employ this physics structured neural network model, when we satisfy given physical laws, we can now train generalized model over the following validation and test set, which are like 20 days into the future on open loop simulation. So now this provides us like great modeling capabilities and generalization, because we are leveraging both learning and physics at the same time, while still learning from relatively small data sets. So when we have this model, can we do controls? This is a simulation experiment when we assume the physics emulator of the buildings. In this case, the 6-zone office building model. We collect like 1 month of the simulation data. We learn this physics constraint model of the building behavior, and we plug it in again in this closed loop system dynamics. And the objective is now to learn the control policy, which is parameterized by the neural network, to solve this optimal control problem offline, such that we can deploy just the neural network online and avoid real-time optimization. We solve this economic model parity control problem when we minimize the energy cost and satisfy control action and state constraints. So to quickly give you an idea how the simulation works, here we have the trajectories of the 6 zones that should satisfy the prescribed temperature bounds. And on the right-hand side, we have 6 control actions corresponding to each building zone that needs to satisfy the bounds on the control actions. So what we are presenting here is a proof of concept that we can use this differential programming to learn offline control policies and system dynamics model just based on the observation of the system. in relatively computationally efficient way without needing large amount of data sets. So here I want to conclude and summarize the differential predictive control is really just the combination of the physics-based classical model predicting control with differential programming that allows us to learn system dynamics model, control policies while satisfying state input constraints. It's very favorable for embedded implementation on edge devices because all the computation is done offline and the online implementation is just evaluating these trained neural networks. And it has nice theoretical connections with classical control methods. So for those of you who are interested in more details, please check our papers and open source libraries which we are building to support these differential programming frameworks for wide area of applications in energy systems. Thank you very much.
Thanks, Jan. And thank you very much. And pretty exciting. A lot of, it'd be great to see how these things get applied and what the results are. So, and I'm sure we'll be talking more about it as we go along today and the next few months. So with that, let me turn it over to Pen Zhao, who's the last speaker. And Pen, you have the floor. And after Pen finishes, we'll come back to our discussions.
Thank you, Ram. Can you see my slides and hear me talking now?
Yes, we can, Pen.
Great.
Yep.
Yeah, great. Thank you. So great presentations, and thank you very much for all the speakers. And so my name is Pen Zhao, and I'm a technical lead in the IPRIS Advanced Buildings program. And I'm going to talk about a project that's going to be funded by IPRIS AI.IPRI, and it's going to be on the AI machine learning applications and demonstrations in grid interactive efficient buildings. What we are seeing, looking at right now is, our electric grid is going to be decarbonized, and it basically changes the way how electricity is generated and consumed significantly, because we know that the growing share of wind and solar got interconnected to the generation mix, and also mentioned the electric vehicles. And so EV charging is becoming more and more significant load, and also customer-sided grid-scale storage are going to be interconnected more and more. So we definitely need larger and larger portfolio, flexible and cost-effective demand response resources to address those changes to the grid. And buildings are cost-effective and can be very flexible to reduce shift and modulate the load to support the decarbonized grid. And here is basically a framework that shows our principal research areas, and we consider smart, connected, sustainable, safe, and flexible are the 5 principal research areas around commercial buildings. And we consider the smart and the connected are basically the technologies to achieve the goals of flexibility, safety, and sustainability. And in particular, in all AI projects, we are talking about the smart, or AKA the AI, to integrate, optimize the connected technologies to deliver the flexibility and the sustainability goals. So the project, or maybe AI project, we have these goals and objectives. So the first goal is a digital twin demonstration for fault detection, diagnostics, and the prognostics to improve the awareness of AI in buildings for energy management. Because they found one key barrier for technology adoption of AI in buildings is actually the lack of understanding of AI in building management. And so we wanted to demonstrate a technology provider's technology in digital twin, so that they can showcase to our members and the visitors to IPRIS building, and also help the facility management to use the digital twin technology. The second goal is to demonstration of data predictive control for grid integrated buildings. So this is going to be a demonstration in a small commercial office located in the San Francisco Bay Area. And we will demonstrate the integration and optimization of distributed energy resources and demand response to maximize the values of buildings and its distribution grid. What they are going to demonstrate is data-driven models for load prediction and also so that the data predictive control model is going to be replacing the historically the physical rule-based models. So to demonstrate accelerated algorithmic scalability. And also the field demonstration will be covering solar plus storage plus flexible loads. So it's to demonstrate the potential of adding other elements such as EV charging to the mix. So potentially repeatable and scalable successes in deployments in future projects. The third goal is a high fidelity data sets of full operation conditions for flexibility. So this is more focusing on a demonstration carried out in April's Charlotte office building 3. It's a large office. And they have been collecting 1 minute data from the building automation system for the last 4 months. And we will explore how to collect data in the load flexibility modes. So this will support building controls and distribution resource planning. Last but not least is the technology knowledge transfer. In the end, we will deliver results. One is a simulation testbed, the other is a field demonstrations. When we do this, is not to kind of commercialize what they are developing, but they take a learning by doing approach. And we do this to identify barriers and accelerate technology adoptions. In the end, we will transfer the technology and knowledge to our members and people that are interested. So I'll move on to, so before I get to the demonstrations, first I will look at the demonstration sites for research, development, and demonstration. The first demonstration site is April's Charlotte office, and it's a large building of 115,000 square feet of constructed area, and for actual usable space is 1,000 square feet. Most of the building is served by the variable air volume system with gas furnace and air handling units and packaged cooling, electric reheat, and terminal boxes. But there are also some offices and conference rooms, and also the cafe area served by the individual package system. The building automation system is the carrier iView. We also have another small office. So it's 23,000 square feet, not very small if you consider medium commercial is defined above 25,000 square feet. So it's right on the boundary between small and medium. And it's a very typical office, and it used to belong to Boy Scouts America, but recently it's sold to Red Cross. And also the unique about this building is that it has a fully integrated, interconnected solar plus storage system to the PG&E's distribution network. And they are developing supervisory control to orchestrate and optimize the solar storage and flexible loads. And those DERs and systems are leveraging the California Energy Commission funding to put those systems on the building. The first goal of the project was to demonstrate a digital twin for fault detection, diagnostics, and prognostics in April's Charlotte office building 3. And because we found one of the key barriers for AI to get into buildings is not really an engineering challenge, but more of lack of building owners and building operators' interest or understanding. So we want to demonstrate that AI is a tool that actually can improve building operations and so proactively inform operators about abnormalities or faults instead of, some people may consider AI to cut jobs and replace humans. So it's actually providing the benefit to them. So and also the FDD platform is going to be providing the information to the building operators before things fall apart, maybe between the building operators' annual checkups. So the demonstration of this platform will be displayed at the Charlotte office building, and at-risk visitors and employees can come in and take a look at the platform whenever they need. So here is basically what it shows. The platform is developed by a company called the R&D Technology Group. It's located in Texas. It's taking 1 minute data from the Calvary Air View. What it does is basically first collects data from all the data points from the building automation system. Then it establishes this causal relationships between those data nodes. So then it will be based on the causal relationship and also the ranges of each data, the typical ranges of each data, and then it will detect anomalies or faults. So for example, the picture on the left, the lower left is basically the yellow ones are the ones that basically outside of the typical ranges. They will show you those are anomalies, and then it will infer root causes. Basically on the right above picture, basically the arrows basically pointing to where the root causes are. If a certain data point is considered either is out of the typical range or is have some faults detected. So again, like I said, those are currently we have already 4 months of data collected, and the system is operating fine. So we are waiting for Duke Energy's 1 minute AMI data. So once we get AMI data from Duke, and then we will have the system go live in our Charlotte building. So the next goal of the project is to demonstrate data predictive control for grid interactive efficient buildings in a small office. They have the solar storage system fully interconnected into PG&E's distribution grid since February this year, and we have the energy monitoring of the solar and storage since April. But if you look at circuit level load monitoring data, that goes back to mid 2019. So overall, we have about 2.5 years of high resolution data at the 1 million level from this site. So the DER system shown on the left is what we have been installed on site, fully optional already. So it can be basically simplified into the diagram on the right. So what it is a solar plus battery plus flexible load system with two-way flows of power with the grid, and the arrows basically show the energy flows. And here the AI piece comes in. It's basically sits on top. What is basically just to intertwine the cyber and physical systems. The supervisory control that we're developing is basically a high-level control that coordinates the battery management system and the building management system. So we will demonstrate how to overcome the challenge of scalability in small to medium commercial buildings, because there are many variations in smaller buildings' energy systems, and we wanted to develop a scalable and open source energy management system that can be tuning the controls itself to match the needs of different customers. So one thing I have mentioned, could be a challenge, but also could be potential opportunities, the change of site ownership from voice calls to write calls. So it will be completely different ways of operation once the owner change, and possibly also adding some new refrigeration loads to the base load. So it will be a good test of the AI to adapt from one scenario to another scenario because of the change of site operations, and also based on data it's being trained into. So we will deliver the results. One is a simulation, the other is a field demonstration. So currently we're looking at simulations right now. And so this slide shows the architecture. So we establish the data-driven models of battery state of charge, and also building loads prediction, solar generation forecasts, building thermal models, and occupants comfort models. And then they put in boundary conditions, for example, energy charge, demand limits, comfort bands, battery charge discharge rates, and also the state of charge of battery in order to keep certain critical load backup, things like that. And then they will achieve some global objectives. So, for example, minimizing of energy cost demand charges and improve solar self-consumption. Then the output are basically XML files of optimized set points that are sent into the building management system, battery management system. So it will be a 24-hour repeating cycle, and day after day, and every day it's going to be optimized. So that's basically how we do this. The third goal of the project is to collect high fidelity data set of full operation conditions. So this is more of talking about using the Charlotte Office Building 3 as a demonstration testbed. So Berkeley developed a orchestration module that acts as a translation layer for data collection from the carrier airview system and our contractors' digital twin platform. So it basically allows operation data to be collected from different HI components, such as heat pumps, package RTUs, air handling units, and sensors, and through the carrier airview. And then we have the data gets into our database, and so we can do energy monitoring and measurement verification. And you can see the pictures on the left. It's basically the visualization of our building 3, and it shows the temperature, relative humidity, CO2 levels. So those are the data. But then we have data a lot more than that. It also includes the pressure and whatever in the duct work and all that. And so then we can also set the sampling intervals. And what we are getting data is that all the data we requested at 1 minute level. So we have 1 minute level of data from the BAS. So from the last slide, we were talking about what data collected from the building automation system. But to be clear, the data set that we collected from the BAS or carrier airview is basically describing the building's normal operation range. So what about data in the demand response range? To make a building an intelligent element to be integrated into the grid, we really need models for proactive controls. But the fact is that machine learning or data-driven models can only predict as far as the data set that the AI is trained based on. So the question is how to collect the building operation data in DR modes if the DR do not happen very often, or the building doesn't really have prior experience of participating in DR. So typically you have two methods. First method is basically you have data collected from other similar building systems in the past, or you have done some lab test data. But this basically, if you are Enernaut, you're a demand response company, or maybe you're a national lab, you have a lot of equipment tested in a lab, then you have those data. But how about you don't have those data? So what we are doing is in method 2. So we are developing a AI algorithm. We are a machine learning algorithm to basically we are going to excite the demonstration building along the learning directions, the data collection to fully explore the data space, so that way they can expand the normal operation range to the demand response range. And it's worth noting that typically the demand response range is not a linear trajectory based on the normal operation range because of nonlinearity of the system. So you can see that the dots are nonlinear if you compare to the data you have. And typically, when you in large commercial buildings, you are going to inject or maybe you want to perturbate the buildings by multiple set points, that possibly zone temperature set point, static pressure set point, supplier temperature set point, so on and so forth, into demand response. And you know that for the same temperature combinations, because of weather variations, you will definitely result in different energy consumption. So for example, for the same zone higher temperature, if it's a hotter day in the summer, you might have a higher energy consumption. In cooler day, even the same temperature set point, you have a less energy consumption. So you end up with different weather blocks of because of the for the same temperature set points. And moving forward, you're probably also looking at the weather blocks, occupancy blocks, and grid interactive objective blocks. So those are the things that they are exploring with Drexel University. So I want to so the last slide very quickly is that for the digital twin, we'll go live at the Charlotte Office Building 3 as soon as we get the AMI data integrated. And for the Boy Scouts America building, they will deliver simulation results by this year. And once the Red Cross is moved in and they get their retrofit finished, and they will demonstrate in the field. For every Charlotte building 3, they will demonstrate and expand active learning algorithm to collect data sets. And then they will deliver what we learned from this project by December 2021. Thank you. That's my presentation. Thank you.
Thank you very much. And thank you to all the presenters. So we are about 6 minutes behind, or actually 10 minutes behind. So I'm going to quickly touch on 2 audience questions that came in on chat, and then we're going to have a couple of quick discussions after that. So Jane, I think the questions that came in were for you. And so the first question we have is, can you give more details on the supercomputer used to train these models? 10 hours seems far too long if you're using the right GPUs.
First of all, we weren't using, I mean, this is just a standard supercomputer. So it's, well, not standard, they aren't standard. It's the Argonne supercomputer. And it was 3 hours of wall clock time to do the training. And it was on a year's worth of data. So it wasn't your typical training environment. It's a hyperparameter search that, it's a package that Argonne created for doing the hyperparameter search. So it's not your typical, GPU machine that you typically work on.
Thanks, Jane. And where can we learn more about these simulation tools and studies? Do you have any open source libraries or?
Yeah, we've written. Well, we haven't. It's hard to open source stuff that runs on supercomputers because everything's different. But we have papers written that you can look up. So if you just, in particular, if it sounded like the interest was in the DCRNN training, that we've written 2 papers on that. First on the building of the model, and the second is the transfer learning work that we did. So, so you can look up, you can look me up, and you'll find the first author, I believe, is Prasanna Balakaprash at Argonne National Lab, and that explains the whole training process as well.
Thank you, Jane.
Mm-hmm.
So I know it's like 5 p.m. on the East Coast. So those of you who are staying on, thank you very much for your patience and for staying on. So I wanted to invite a special guest today. It wasn't planned, but I'm going to see Erica. Are you still on? Are you able to talk? So just a quick introduction to Erica. So she works at the Department of Energy at the Building Technologies Office, and she was the brains behind the Connected Communities research that's going on and the grid efficient buildings research that's going on at the DOE. So, Erica, why don't you maybe give a little introduction, talk a little bit about the DOE's work and focus, and hopefully that'll lead to more questions.
Thank you, Ram. I certainly can't take all the credit for connected communities, but it has been a big part of my time over the last 2 years. And we announced 1 year ago the funding opportunity announcement for the connected communities, FOA. So that really was when we started to put this into motion. And I can't wait to make actual selection announcements and start testing this out. But the big concept behind connected communities is really, really looking at how do we integrate all of the available resources we have, whether it's data, from the transportation sector, knowing when people are coming and going to be in buildings. So not just taking data from the building and only knowing when somebody walks through that door, knowing ahead of time that they are going to walk through that door really enables us to optimize, right, pre-cooling or preheating for these spaces. Same thing with commercial buildings, knowing when a conference room is going to be in use and an estimate of the capacity based on, say, your Outlook calendar and how many people are booked into that room. So taking data from multiple sources and then integrating DERs like solar or vehicle charging, and really figuring out how do we optimize this system to, one, first and always provide a comfortable and productive occupant experience, right? The buildings serve occupants first. Two, how do we minimize the overall energy use of these buildings in order to reduce the cost, right? So that's an economic savings to the building owner operators. And how do we reduce carbon? So this is where it becomes incredibly important to not be able to just reduce our load. Reducing our peak load is critical for reducing carbon impact of buildings, but also enabling the grid to have more variable renewables by providing grid services in demand response, that flexibility. So being able to predict when that is going to be needed, either from a grid signal that the grid is predicting day ahead. So we need all that data and analysis from the grid side to know what it's going to be asking of the buildings, to know what the weather prediction is, to know what that impact is on the building, to understand that building model, not just from the perspective of, yes, this is a building, it has 4 walls, but knowing what its thermal mass is, knowing how much radiance it's getting, knowing when its solar is going to be available, when its battery is going to be fully charged, and really being able to optimize that system. So there are a lot of questions that I think are ripe for AI and ML in this space to really help us with that optimization. And we have work in this space across the portfolio. A few of the projects are in demonstration, but a lot of them are still in the labs and simulation. The idea here is really to take that technology, move it into the real world with a mix of commercial and residential buildings, and looking at how can we make a system that is greater than the sum of its parts in terms of performance and flexibility and its carbon reduction. So some of the key things you really want to look here is, how is this going to be economically scalable? What does the business model around this look like? What is the experience of the occupants? Are they comfortable with it? We talked about building owners as well, but also the occupants, not just the building operators. How do we communicate what the building is doing? We talked a little bit about that earlier with the natural language processing, and really trying to understand how that works in this greater system. And trust and control. So can the occupants still override if they're uncomfortable? I think we've all been in an office that's too hot or too cold. So not just looking at it from what is the perfect optimization, but what is that optimization that takes into account all these different objectives? And there's just an enormous amount of opportunity here in the AI and ML space. I think those are my key points. Ram, is there anything I missed that you thought I should hit on there?
No, I think that's great. And maybe actually one thing, maybe touch on the role of transportation in the connected communities, in terms of how that connects into your vision.
Yeah. Certainly, we have been working very closely with the Office of Electricity, the Vehicles Office, and the Solar Office on this because of that integration aspect. And this is understanding the vehicles. How do we optimize when vehicle charging will occur in a fully electrified vehicle market in order to minimize the impact, but really also looking at opportunities. As I mentioned with Jane's work earlier, of understanding what are the traffic flows, when are those occupants going to be arriving, when are they going to be looking to charge their vehicles, and considering that as part of that demand management scenario. We actually have a very interesting project with DFW. They're designing a new wing for the airport. I think Jin is on from NREL, who might be able to talk more about it. But we're actually in that project looking at that optimization of how do we bring in information on arrivals and departures and traffic to know when people are going to be arriving at the airport, and how can we optimize this multi-megawatt energy user using AI and ML.
That's great. That's a mega community in itself, right? It's
I mean, if you think about an airport, often they have hotels connected, they have foods, they have restaurants, they have stores. So it's just an enormous energy user.
That's great. No, thank you, Erica. And again, I mean, so for some of you who work with me, you know that I'm good at calling people out on the webcast. So thank you for being a good sport and coming on to present your vision. So that was very, very helpful, because I think it sets the stage, right, for what we are trying to do here and what our other speakers have also discussed in terms of the data and how all of this connects together. So thank you so much for coming on, Erica. And you're welcome to stay on for the panel. I know it's late, but if you want to stay on for the next 15 minutes, 20 minutes, and chime in, right, as we go through the rest of the discussion. So thank you.
Good until my 5:30 meeting.
Yes, thank you. With that, let me also turn it over to our fearless leader, Jeremy Renshaw. Jeremy, are you on?
Yes, I'm here, Ram. Can you hear me?
Yes, we can. Thank you. So why don't you take it away? Give us your impression of the session, what you wanted to get out of it, and where you want us to go.
Yes, so this has been great. So thank you, Ram, for putting this together, and a special thank you to all of our speakers and the great topics that you've brought to us. So we've talked a little bit about some of the technical areas that we're looking at, and thank you, Erica, for jumping on and kind of broadening our vision into other areas that we should be thinking about. So really what we want to focus people around is how can we make real progress in these areas? And the way that we do that is working together. No individual organization, institution is going to make all the progress we need as fast as we want. As great as the people are, as great as the work that you've heard about today is, we really need a group of organizations working together in unison to get over the R&D valley of death into implementation. And the best way that we do that is combining all of these great academic organizations, whether they be universities, national labs, EPRI, or others that are developing these technologies, or AI vendors that have great solutions. But we need to marry those with utilities and end users and find ways to do pilot projects, demonstrations, to be able to benchmark these technologies to eventually scale them up into enterprise-wide adoption across these large organizations. So the real purpose of these grand challenges is to bring people from all of these different organizations and all of these different backgrounds and companies together to be able to work together. And we've done this in the past where EPRI, DOE, utilities, and other organizations would team up together to focus around specific areas. And those are always very beneficial because these end users often have a different perspective than those on the technology development side of how they would utilize them. And so early on in the process, if we make small tweaks to how we develop these technologies or how we use them or how we design them, then that can make big impacts on the back end of how we use them down the road, so that we are able to avoid getting to the end of a R&D project or the end of a process the money's spent, the time's gone, and then we try and throw it over the fence, and someone says, well, I'm never going to use that because of, this or that or the other thing. So what we're trying to do here is early on in the stage, get everyone working together, have the same focus, have the same goals in mind, so that as we progress through these various different projects, that we can have a greater likelihood of success and have everyone working together. So what we're planning on doing for this is a number of different things. So we're planning on hosting this summit meeting once per year. We'll be rotating from this year it's virtual. Next year we plan to go to Europe and then continue rotating around the world after that. But also have some periodic check-ins where we hold each other and ourselves accountable to the progress that we're trying to make, as well as reach out to those who we need to be able to help us, whether you're an AI developer and you need to tag team with utility, whether utility you want to get involved with an academic or a startup. We have ways of connecting people together. And so we'd like to utilize these networks that we have and help each other out to be successful and find those win-win-win situations where everyone benefits by working together. And we're not really trying to take advantage of one another. We're trying to work together for mutual benefit. So I think that's really the intent of these grand challenges. So thank you, Ram. I appreciate it. And I hopefully I didn't put you any further behind or too much further.
Hey, we can always catch up, right? So we're gonna keep meeting on a regular basis. So everybody who's staying on, I know really wants to work on this. So we'll catch up. So thank you, Jeremy. And I think kind of leaping off from there, right? We talked about the goals, right? What we want to do is really kind of understand what the research questions are. I think all the speakers and you've kind of outlined some of the research that's going on, some of the challenges. But by the end of the day today, we want to end up with, okay, hey, here's what we're going to do next steps in terms of the cadence. Here's the type of research questions we want to address. And hopefully over our engagement, right, in the near term, define what they are, what the barriers are, and how data, customer systems, and utility grid all come together. Sorry. With that, let me just get back to the panelists for a few minutes, and then we'll come back and do the wrap up. Okay. So question for the panelists. So we talked a lot about the data. We talked a lot about simulations. But we know that there's a challenge in being able to take real data from customers, from customer systems, and use that for applications for example, on the grid side, on understanding the grid or trying to do grid planning, right? And there are challenges with regards to privacy, with regards to ownership, and with regards to the cleanliness of the data, right? So I want to start with Jane. Do you want to take it from here in terms of how do you see the users of the data, whether it's the utilities or the cities, and the people who actually have the data? How does that transfer happen? What are the challenges you're seeing? How do we get to the point where the users are actually able to use the data that's being generated to be able to do whatever processing we need to do?
Good question. I'll try not to take too long because it's a deep subject. I used to be the chief scientist for HERE Technologies, so I sat on both sides of the table as far as data goes. So we had a whole lot of probe data, GPS probe data, and we often didn't give it to anybody. And now I'm on the other side in the academic MPO side, and looking for data that I can't find any, or I have to purchase it, or there's some provenance behind the data. It's been aggregated, or it's been used. Real data has been used to create a synthesized set of data. So we have a whole lot of work to do on the front end of the data side, to go from raw data to data that can be used by multiple people interested in using the data, with open communication about the provenance, about what cleaning was done, how it was aggregated, what was the assumptions behind the cleaning that was done. So just for example, GPS data has all kinds of crazy, speeds and accelerations that are not physically possible. So you have to apply a vehicle model to the data to make sure that you're not generating data that doesn't make sense. You don't have cars flying, at least not today anyway. They will be soon. And so there's a whole lot of work that has to be done on that front end, and it needs to be open to everybody so that you know what's been assumed in the process. And right now, to be honest, and it's not PC, all that data is locked up in industry data sets that aren't shared. And everybody stands behind the PII problem. So we need to solve the PII problem. We need to solve, we have to come up with mechanisms to get that data out of those silos, because cities need that data to understand what's happening in their city, so that they can make good decisions about planning and operations that will help everybody in the city and build a better quality of life. So there's a lot of work to be done, and breaking those silos is going to be really, really difficult.
Thanks, Jane. Yeah, that's you're right. As the scale gets larger, right, it's harder and harder to get it.
Right.
Let me turn to Zoltan. Like, I mean, you've done this. You showed us this great microgrid with the different building types, etc. Right? And how do you go from modeling to using data to verify it? And then when you actually presented the results, they were very interesting on what the different teams came up with. But what was the data challenges? What data did they finally end up using? Were different teams using different levels of data? Any insights on that?
No, so the data, that plot I showed you was literally 2 weeks old. So we have not had time to look through individual solutions that the contestants have used. But you're right. I mean, the challenges in buildings in many ways are like not even where Jane is. Like we are at the point where, oh, building managers, what do you want data? Why do you want data? And then it's like this kind of discussion that we try to improve your building. No, the building's great. No, wait a minute. It's, like that kind of discussion is what we're having daily. And the examples that Penn showed are fantastic, because those are the ones that, oh, look, you can do something with an actual building. It is a resource. But I don't think the industry has made the connection yet to like not even monetizing yet. Like that's why I said we're not even where Jane is, where, oh, just give us money, we may give you some data, but they're not even at that point where they could put a dollar amount onto the data, and then we can start talking about cleaning that data set. So in many ways, it's very, very hard, to circle back to your question, to validate what I showed. So we have to rely on, that's why we use the DOE models for the buildings, because they have some validation behind them. They do make sense. We run different combinations, so we have some fidelity in them. And then, people like Jan, who do physics-based, at least we know physics are okay. So then that kind of like makes sense. But I think we're like, I won't say miles, but there's quite some step before we can get to sharing widely data sets.
Thank you. Yes, Jane?
Yeah, I have one thing I want to note, that just cleaning data can cost you a huge amount of money. and people put value on data sets and they store them away. And these data sets, particularly in mobility, are highly redundant. I mean, we need to work on algorithms that take the data and shrink it into the key event moments in the data, and allows us to mine it more effectively, again with an open approach to it, so you know what's been done to it. But a lot of people think they have highly valuable data and want to price it high, and it's really, there's like a few little gems of information in there. It's like data, it's like gold mining. There's a few nuggets in there, but a whole lot of dirt.
It's a lot of panning. Jan, your thoughts and comments. I mean, you are using physics-based models. So how do you see the role of data in both enabling your model, but also the challenges?
Yeah, exactly. Look, I will just echo Zoltan and Jane that especially like in the building space, your data is scarce, and the quality is not very high, right? You often have like missing data points and the data cleaning, lots of work. So that's why we believe like combining data with some physics will give you the benefit of the both, because you can fill in the gaps when you don't have this real-time stream of the data. And you can do these estimates using these physics-based models. And often when you don't have the physics-based models, like at least full knowledge, you can use that very little data to estimate a handful of parameters instead of like hundreds of thousands of parameters of black box models. So that's our perspective.
So what kind of data would you need? So you're saying that, hey, we don't have as much data, right? What kind of data would you need? So if somebody is looking to create demonstrations, maybe this is something Penn's working on, right? Like, hey, what kind of data would both you and Zoltan need to be able to enable your models?
Yeah, so it depends on applications. When
Right.
you are focusing on the energy forecast, like you would like to have time series of the energy use of the different utilities. If you are talking about the temperature forecast instead of buildings, this thermal buildings model, you want to have the measurements of the temperatures inside the building zones. Maybe if you have some thermocouples inside of walls of weather forecast, historical data set. And when we are talking about learning these control policies, with reinforcement learning, you need to have this emulator model. So having this actually active perturbation of the system, which either comes from experimentation on a simulation model or perturbing the real system, is also pivotal to the success of these learning-based controls.
So if you were to maybe try to paraphrase, right? Just so if you have a demonstration, you want to create demonstrations where you're getting AMI data, maybe AMI data from the utilities. You're getting sensor data, temperature sensor data, right, from the buildings, and the capability to kind of change the operating conditions, perturbate them, so that you can see how the buildings are responding. Is that
Exactly.
a appropriate description? Okay.
Yep.
Okay,
Such that
no,
you
that's
can
good to know.
connect these physics-based points, like you build your physics-based model, you know, like for this causally interconnected, but also like you verify what are the sensitivities of these physics-based variables between each other.
Okay.
I want to make another point, Ram, if I have 1 minute, which goes in the same direction of leading, physics-based models. But last year, with a colleague of mine in Singapore, we organized a Kaggle competition on forecasting energy, basically. But, we just provided lots and lots of data, hourly data set, cleaned up, all those things. And so come up with models to forecast energy demand, basically next hour or the next 2 months or something. And so there we analyzed the solutions. But what became very clear is that the top 10 or so, the top 3, I think, of the solutions all understood the physics of the problem, all understood the energy. So you can't just AI your way out of this, like in a black box way, basically, right? You have to understand what you're doing. Otherwise, it's just as good as, let's say, linear regression, and then not, right? You don't make any value on top of it. So there are a lot of cool techniques out there, but you have to know why they're useful and why they're not useful. So.
Okay. No, that's a great point. And I think if I can, I'm trying to kind of absorb it. But yeah, go ahead. Go ahead. Yeah. Say something. Sorry. I'm just thinking, okay, hey, where does data analytics end? Where does AI begin? Right. So there's that where the transition, and that might be different for transportation versus buildings, right? It might be different for the different use cases that you're trying to solve. So I mean, I think those are things that we really have to figure out as a community on, more importantly, I think, on what data we absolutely need to be able to prove all these models. Because Jane, to your point, yeah, you could just get a ton of data, pay a lot of money out of it, and then you'll get these little nuggets out of it. So that's a great point. So I know we are kind of about 3 minutes away I think this actually probably like what you're saying, both Jan and Zoltan, what you mentioned around the demonstrations. Pen, I know you have the demonstrations going on. Do you have any, can you take like 30 seconds to talk about the type of data you're getting from the demonstrations, and then we'll go to closeouts? Okay. I don't know if you have Pen. Pen, you're on mute. Okay. Yeah, that's okay. I think we're 2 minutes away. So one thing I also wanted to mention, I think part of the goal of the Connected Communities demonstrations was actually to get the data so that we can feed into the models. And I know many of you are probably involved in those proposals too. So I think we are moving into that realm where we are now like, okay, hey, let's start getting the data so that we can pull out our models, and then let's do the physics basis before we get into AI. And that really kind of, I think, is the step forward for us. So just to wrap up, I think next steps, what we would like to do, and is as part of this grand challenge, is start creating this community where it could be maybe just having informal monthly get-togethers, meetings, etc., so that we can start defining the problems. Especially, I mean, given as EPRI, right? We really want to define the problems in the way that it impacts decarbonization of the electric grid and decarbonization of the economy, and outline those problems, understand how much data we actually need, and figure out these data synergies so that we can figure out how we can get that in to solve these problems. So, so what we'll probably do is follow up with all the participants and try to set up some kind of a community forum so that we can start engaging with all of you as practitioners to understand what is available, what we need to do, and how that connects back to the larger energy system. And using that, we will move forward. So, Jeremy, are you on? Do you have any last comments before we close? You might be in the other session too. I know.
Yes, I'm still here. Let me take off my mask here so you can see me. No, I think you've got it, Ram. That's exactly what we need. So, let's get together. Let's find a way to meet together regularly and check in, hold each other accountable, but also help each other out. So I think what we'll probably be doing is sending out the meeting materials afterwards. And as a part of that, we would definitely encourage people to reach out, and we'll work with Ram and others to identify a lead for this grand challenge. We have the participant list of people who are here as well as who are interested in getting involved. So we will provide a way for you to reach back to us, and we'll make sure to share the contact information of those who are on here to the person who works with Ram on this grand challenge going forward. And we'll get everyone involved and invite you to these check-in meetings. And we also are looking at coordinating with another event that goes on maybe about 6 months out from now. So if you have other events that you think would be good, we're trying to minimize any additional travel burden on people. So we don't want you to travel any more than you need to. So we can find another event to tag team with and work together with in this smart communities area. That's what we'll be doing to be able to get people who are interested and involved already in this area, and have maybe like a dinner meeting together, or maybe a session in that conference or event to be able to get us all together and working forward and pushing forward in these areas. So thank you, Ram. Thank you.
Thanks, Jeremy. And we want to really thank all our presenters today and the audience who's been engaged as we start developing this community, right? It's AI, data analytics, but for the grid edge, and figuring out how buildings, transportation, cars, everything comes together to enable our energy future. So thank you. Thanks, everyone. And thank you for your time. And for those of you on the East Coast, thank you so much for staying late. So, yeah, thank you.